A'udzu billahi minasyaitonir rajim. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And a very good day to everyone uh, under the subject sensors. Now we move to the next topic for this subject, which is we want to look into the temperature measurement. Before I go further, so this is our lesson outcome for today. So I expect you to that all of students can able to discuss and explain the detailed and basic element and sensing mechanism for temperature measurement. And then the second one, I expect that after this class, you're gonna know how to analyze the output signal from any temperature sensor. So this is actually the content for this lecture for today. I will start with the introduction. I will introduce you about the temperature measurement, and then we're going to look at the definition of the temperature, and then we're going to look into the scale and standard for the temperature, and then after that we're going to look into the available sensors and also its mechanism for the temperature measurement. So we have three types of methods that we're going to use for the temperature measurement, which is non-electrical, electrical method, and radiation method. All right. So now, as an introduction, temperature is a variable. It's a variable that we measured. It can be as a control variable as well, and it's used in many applications. It's very important in engineering. Basically, we use it for the governing parameter that can govern a few parameters. We're gonna have in parameters we have a lot of variables, as we mentioned in the previous topic. Parameters is the combination of a few variables, and for some applications in a parameter there is a variable temperature that very important for that parameter. For example, in the use for in the thermodynamic parameters in and also in heat transfer parameters, when we have a certain thermodynamic and heat transfer parameters that always used in a power plant and gas turbine and so on. You're going to look this one in the topic thermodynamics and heat transfer. But in those topics, temperature is very important variables, and also temperature is a very important controlled variables or parameters in some processes. For example, in aircon, it's very important for us to, of course, if you want to have a very stable temperature, we're gonna control the temperature. And also in some manufacturing process, it's very important for us to control the temperature. We not to have a very high temperature and not to have a very low temperature. Also in nuclear reactor, we have to maintain temperature because in nuclear reactor, it's very important for us to make sure that there's a coolant system to cool down the core reactor. If we didn't properly cool the core temperature, the core reactor, it will have a risk of explosion. So that's why we need to have some control mechanism, which is it is temperature as the control parameter or control variables. All right. So next, we look at the temperature definition. It's actually a degree of hotness or coldness. It tells us the level of how hot that body or environment, how cold the body of environment. According to the Zero's law of thermodynamics, if we have two bodies in thermal equilibrium, and then they have the third body, they will automatically in thermal equilibrium. whereby these three bodies will have a same temperature, so that in other words, there's no heat transfer until no heat transfer. When that bodies close together, come together in the system, it will have a same temperature because of there's no more heat transfer between all the bodies. At first, you have a movement in terms of energy, and after a few minutes, a few hours maybe, it will have no more heat transfer, and it will maintain at one temperature for all the bodies. But that's what Zero's law tells us. And then, of course, if we deal with temperature measurement, we need to have like a standard measurement, a standard values, so that we can use that standard values for calibration. For example, if we look at the length, we have 1 meter length. So what is 1 meter length? It's actually a measurement of a standard object that have 1 meter length. So that object is a reference to all measurement. So 1 meter of that object. For example, this object is a pen. For example, is 1 meter. For example, so this is very standard object. So that if we want to measure for 2 meters, 3 meters, we're going to use this standard of length to measure 2 meters, 3 meters, and 4 meters, and so on. The same with the temperature. We need to have a standard values that we can reproduce every time. Like the 1 meter length, we can fabricate some reference length. Some object that can be a standard for measurement, 1 meter length, and then that one should be sorry, I didn't have ruler here. So a ruler is one of the reference object that can be used for the length. But for the temperature, you need to have some standard or some situation or condition that we can reproduce all the time. For example, we have fixed point according to this table. For example, we have a triple point of hydrogen. It can be reproduced by maintaining some pressure and temperature. And this triple point of hydrogen always occur at 13.8033 Kelvin, a very low temperature, or equal to the negative 259.3467 degrees Celsius. But hydrogen is considered as a very low temperature, but it can be done. We can produce the triple points of hydrogen. The easiest one is we look at the triple point of water. This one, triple point of water. Look at that. Sorry, this one. Sorry. So triple point of, not that one. Can I erase? Okay. Okay, triple point of water. So it is about this one. So Kelvin to 73.16 or 0 degrees Celsius. So triple point of water is easy to create, which is you just take an ice, take out from the fridge, the freezer, and put in a glass of water. So at that time, you will have a three phase of water, which is we have a solid phase, liquid phase, and also gas phase. So that one, it will have a temperature of 0.01 degrees Celsius or 270.16 Kelvin. So the same with other 3 points. For example, 3 points of oxygen, 3 points of neon. You can use this fixed points to be as a calibration points lah. It always can be reproduced. It's easy to be reproduced, depend on which application that you are looking at. Okay, now sorry. So the scale that we're gonna use for the temperature measurement is Fahrenheit and Celsius. It is in metric units, or in Kelvin. Celsius scale is Kelvin in terms of absolute value, absolute scale, and for the absolute scale for the Fahrenheit is a Rankine. Rankine. Of course, in us in Malaysia, I think in Australia, in Asia, usually we use Celsius, metric unit. Celsius as the temperature measurement. All right. So the conversion factors for the measurement, for example, to convert between Kelvin to the degree Celsius is written in the slide. I will not go further on this one. Nowadays, we just can simply use calculator. They have all the conversion. Also, you can Google, easily can convert from any scale to another scale. All right. So we're going to now finish with that simple concept of measurement. Now we're going to look at the three types of measurement method: non-electrical, electrical method, and radiations. All right. So the first one is a radiation method. For non-electrical method, we look at two kind of non-electrical method, which is liquid in glass thermometers and bimetallic thermometers. So this kind of method, which is not electrical, we frequently use. We use this one in the area that have risk of explosion. For example, in oil and gas, usually they need to have explosive sensors, no spark, no creating a spark into the system. So basically, electrical sensors will create a spark and will have a risk of fire and explosion. So that's why they come with the non-electrical method, which is very easy for the very safe for the risk. For the area that have a risk of explosion. So first we look at the first sensor, which is the liquid in glass thermometer. I think this one is very everyone know how the mechanism of this one. So we have here is a bulb here. So the bulb here have either mercury or any kind of a liquid that can expand with the temperature increase. So it will move in the capillary tube that will show the level of expansion in the capillary to show the level of hotness in that environment. Usually it will use for the environmental temperature, and also it can be used for the liquid temperature. Just dip the area of the what do you call this bulb here, or the tank for liquid. Just sink into any temperature or any gas or any area that we want to measure, and then it will directly show the temperature. It depends on the type of liquid that we use. Some for example, mercury have a freezing points of a negative 37.8 degrees C. So we're gonna use that one above that level. If you use that at the freezing point of mercury, we don't have an expansion. And then for the liquid glass, which is mercury, of course it will need to be above than its freezing point, which is negative 37.8, until to the maximum point for the mercury, which is can be 340 degrees C. But if we add a few more chemicals inside that mercury, we will have maybe higher value, higher range. Maybe it can go up to 560 degrees C. Okay. So the uncertainties for this one is about negative plus minus 0.2 degrees C, or it can also be a plus minus 2 degrees C. The uncertainty for the temperature. It depends on the type of temperature that we want to use. Maybe the design, big or small, or using maybe full mercury, or maybe a combination of additional chemicals inside the mercury, so that it can be used for further. Maybe it can increase the range for the measurement. But all these things will come with the uncertainties as well. And then now we move to the next one. Is sorry, before I go to the next one, I need to mention about the advantage and the disadvantage about the thermometer. So the liquid thermometer, it is really low cost, simple to use, portable, and convenient to look at, because it have different colors. Mercury have a red color, so it can, if we put a mercury inside the capillary tube that have a white color, we can look at the we easily can see how the mercury move, expand inside the capillary. And then the problem is for this method is actually have limited to certain laboratory only, and because of we fill it in the glass container, it will easily breaks. So if it breaks, so mercury is very dangerous. It's not safe for children. Okay, basically if it breaks, then we need to have a hazard control if it breaks. And also one more thing, the liquid thermometer, which is mercury, it have delay time. It's not simply just show the value. It have lagging, time lag, before it can reach the level that can tell us the reading of the temperature that we want to measure. All right, so then we look at these biometric thermometers, which is basically two materials that paste together. We bond together, so that the first one, the top one, is a high coefficient of thermal expansion, and the bottom one have low coefficient of coefficient. Of course, the top one will expand more than the bottom one, because of the top one have high expansion rate. So this is how they both they just put a high expansion on the top and low expansion at the bottom, so that you can have a curve. The equation for this, how to predict the curvature of the bending. We're gonna look. We need to look this equation. So if we have the D, the total thickness between those two metals, and then at the early temperature T1, it have a straight line. So at the T2, it will have a curvature. It will have curvature. So the curvature is equal to D, the total diameter. The thickness, not diameter. The thickness of the both A and B, divided by the difference between the thermal expansion and times the difference between two temperatures. Final temperature and early temperature. So that one, this equation is for the system or the bodies that we know the measurement, the values. But for more generalized equations, this one. So it tend to have a generalized equation. So in this equation, there's no there's no unknown involved here. Okay, so it totally totally depend on the what kind of value we want to insert inside this equation to form a correct size of correct size of biometric materials. So this is actually a very general equation as a guidelines for us to design the biometric materials. All right. So biometric materials have a range of -30 to 550 degrees C. The uncertainties is one only. It have a big range of uncertainties, like we have in the thermometer measurement. It have quite huge uncertainties from either 0.2 plus minus up to 2 plus minus uncertainties. But for the biometric materials, it have only fixed point plus minus 1 degree Celsius. Of course, it have when we use the physical body as the temperature sensor. Of course, it have its own limitations. I think for those who are familiar with this one, they know how to deal with this one to check. The thing is, this is a metallic. Yeah, usually they use this one in the control that have a circuit, the joining circuit. So if the temperature increase or whatsoever, it will have a curve and it will disconnect the circuit. So for this one, this kind of thing make it very good if you want to build a controller, temperature control. For example, in the aircon, in the oven, in the iron, okay, iron, refrigerator, okay. So as an advantage, so it is low cost compared to other type of temperature measurement. The only thing is it have inability to measure rapid changing. So because of it's actually like a static temperature measurement. So if we give the heat, it have a slow rate of expansion. But imagine that we have a very fast temperature coming in, so that sensor not able to catch up that fast movement of the fast movement of the variables, parameter inside the measurement, inside the measurement. All right, so that's the advantage and disadvantage of the biometric. And also, if we look at the liquid thermometers, also have advantage and disadvantage. So you compare both, so then you can have which one appropriate usage for your application. Okay, that one is for non-electrical method. Now we look at the electrical methods. There's two common methods for the electrical method, which is first is the thermoresistive type. It focuses on the resistance of the thermal resistance of the sensor, and then the other one is thermoelectric type, which is it's more to the self-generating voltage or EMF uh, because of we have for the first one, thermoresistive. If we have voltage, it will create either just confused. For thermoresistive type, with the increase of temperature or decrease of temperature, it will give different readings to the voltage. And if you look at the second one, thermoelectric type, with the change of the temperature, basically the increase of temperature, it will also increase the generations of voltage, the EMF. We call it EMF. Okay, so after this, we're going to look at in detail of this one. But this is actually a very common methods to be used. The only thing is we want to make sure that either we secure the sensor with non-explosive box or spark-proof box to make sure that it have no other effect to the system that we want to measure. Especially in oil and gas, we need to pass explosion-proof test, and also it must have spark-free in the system. All right, so we look at further. For the first one, under the electrical method, which is the resistive type, so it is based on resistance. This one also is divided into two parts. Okay, either it the resist sorry either temperature increase, resistance increase, or temperature increase, resistance decrease. It's either one. So we look at the first one. The first one is we're going to look is the RTD. RTD stand for sorry, it will show after this resistant temperature detector, RTD. So we're going to look this one first, and then we're going to go to the second one, which is thermistor. So for the thermal resistance detector, so it detects the resistance. So for RTD, it's going to use this equation. Okay, we have looked into this equation in the previous topic, which is in sensor. So R is the resistance equal to the constant, the resistive constant times the length, and then the divide by the area of the conductor or conductor tu sendiri. So RTD have benefit of very accurate temperature measurement. Of course, resistor also have its own accuracy, but we cannot simply just say this one accurate or not. We need to look at the specification. If the specification shows it have low accuracy, then we can say that this is low sorry. If the accuracy is low from the spec sheet, so we can say it's low. If we have a very high accuracy, so we can say this high accuracy. It depends on the spec sheet about the sensors. For this one, we need to look at the mechanism, how the resistance can be used as the temperature sensor or measurement. We know that in the previous class, when we increase the temperature, it will increase the resistance as well. Okay, right. So that's in the previous one. So we're going to look further this one. So usually, before we go to the mechanism, we can look at the type of material that frequently being used for the RTD. We have the material that have sensitive to resistance, which is platinum, copper, tungsten, nickel. All these things is actually have very high resistive. So the RTD can be used starting from cryogenic. Cryogenic is the temperature, very low temperature. It's a very low temperature for a body, for a material. For example, usually below than 150 degrees C or 180 degrees C. It's very low temperature for a body, and then it can be up to 650 degrees C. 650 degrees C. So you have a very huge range compared to the previous one we discussed, which is the biometric thermometer or the liquid thermometer. The disadvantage is relatively low sensitivity, relatively higher cost compared to other, and because of the construction of the RTD, it's easy to get error. It's easy to get error. We're going to look at this. What's the basic mechanism, concept, or design for the RTD? Then you can understand why it's easy to get error. Honestly, I have deal with the strain gauge. Strain gauge have a Wheatstone bridge, which is the RTD also use the same concept. This makes it have prone to errors during measurement. So we move to the next slide. So usually RTD use platinum because of it have temperature resistance, okay, and then stable for a wide range of temperature. It has resistance to chemical attack and contamination, and it have high accuracy, predictable and reproducible changes in electrical signal. Okay, so platinum is common to be used for the RTD lah. So if you look at this graph, you look at the relation between the resistant or the relative resistance. If you look at here, R over R naught. R naught is the original resistance. R is the resistance after it increase, the temperature increase. So the relative resistance is, it can be related with the temperature, which is the higher temperature, the higher the relative resistance. So if you look at the copper and platinum, they have relatively lower relative resistance compared to the nickel for a same range of measurement. But if you look at nickel, it have a bumpy. It's not linear. At particularly it's in the area of 300 to 500. It have a bump, so it's showing that non-linear area. So that's for nickel. If you look at the copper and platinum, they are actually very nice, very linear. Just now I mentioned platinum is frequently used. It has a very linear curve, very linear line. It can be used for measurement. Accurately can show the value for the temperature measurement. Platinum and copper, but copper is up to the maybe about 600. But platinum it can give up to 800 degree. So we have a large range, starting from the cyrogenic until the maximum for copper 600 and for platinum 800. Nickel, yes, it can up to 800, but it also have a very high slope, so that showing that it have a very high relative resistance compared to the temperature. But the problem with nickel is it have a bump, so we have uncertainties at about 300 to 400 500 degrees C. So if you look at table 8.2, there is more temperature coefficients of resistivity for a selected material. Of course, if you're looking at the lowest one is I think nichrome. Nichrome have a very low low temperature changes compared to the relative resistance change. So chrome, yeah, it's very low as well. The platinum considered very low, but still it always used because of it have acceptable relative resistance. So that one is if we discuss on the curve, if the curve in the resistance temperature curve for several materials. So if you look at the body of the RTD, this is what it look like. We have copper leads as the input, and we have another terminal. This is just for positive negative. Of course, the flow of the electrical come in one leg and then get out for another leg. But it have a coil inside the ceramic container or a metal container. It have inside, they have a like a ceramic former, or this hollow thing, a roll of resistant element. So the rolling of the resistant elements, it depends with the equation that we have shown just now. On this one, okay, it totally relate this equation, and also we can simply calculate which material is is useful. Okay, copper is common, platinum is common. We can get it anywhere, any of the uh, uh, hardware store. All right. So, like I mentioned just now, we need to use a RTD. We need to use a Wheatstone bridge to measure the resistance. So I move. Sorry. This is actually another example of temperature detector or measurement. And then this is actually a equation that involved for the RTD. Like I said, RTD is based on the resistance, so it always measure the resistance, and it relate with the voltage. So it comes with the original equation is the polynomial expansion. So but if we can simplify this polynomial expansion, so we get this one. We have this one as a final one. So we have R is the coefficient, sorry, the resistance that we want to measure. R naught is the early or the initial resistance. Of course, this one is the coefficient. Different material have different coefficient, and T is the temperature that we want to measure, that we want to see, that we want to look for, and then T naught is the original, the earlier temperature. So we have this one, these two things here have interrelated with each other. The rest is just constant. So if you look at this equation, the R increase, so T also increase. Okay, so if we increase the T, it will automatically increase the value of R resistance. All right. So this is actually what I'm talking about, the Wheatstone bridge. If we look at the strain sensor that I mentioned in the previous class, Wheatstone, sorry, for the strain measurement, we want to calculate the VG, the VG value here. I can show the here. We want to calculate this one. From this one, we can convert into value of strain by using equation. Okay, I don't want to repeat this one. You just look into the slide. But for this one, the VG is important for us to maintain the stability or the balance of the circuit. Okay, I will frequently use the word balance, because balance is the key for this one, for this measurement of the Wheatstone bridge. So we have a R1, R2, and R3 resistance, and then Rx is this Rx, the one that we want to measure. So R1 and R3 is the fixed value of resistance. So R2 is the variable variable resistance. We can adjust the value for the resistance here. We adjust the value here. So for example, if we have fixed value R1 and R3, and then Rx is something that we want to measure, of course it's actually it will change depend on the condition. If the body have increased value of temperature, so Rx also will increase. Okay, so if Rx increase, it will give effect of unbalance to the circuit. Also, we will look at this in the next slide. All right. So this is actually the equation. So R1 over R2. Okay, the ratio between R1 and R2. R1 and sorry, this one is R2 actually. Sorry, uh, R1 and R2. This one, this one should be equal to the R3 over Rx. So if R1 over R2 is equal to R3 over Rx, that one we call it a balanced circuit. Okay. If you look at this equation here, okay, the equation here. So R1 over R2, R1 is a fixed value. R1, R2 is the variable. We can vary, we can change the value. R3 is a fixed value according to this circuit. According to this circuit, okay. So R3 is the fixed value and Rx it depend on the temperature that we want to measure. So if this Rx is increased due to the increase of the temperature that we want to measure, so it will create unbalance to the Vg. It will, when it unbalanced, okay, it will have a value, a value 1, 2, 3, 4, 5. If this is balanced, okay, this one ratio, this one is equal to ratio this one, both this one, the Vg will have zero value, because no no current in the system because of resistance balance. So no current working, so there's no voltage lah. Okay. So how to make sure it's voltage? Because the Rx is increased due to increase of temperature. So to make sure it balanced, we need to increase also the R2. Okay, we increase R2 until the Vg is 0. So Vg is 0 means it have balance. So R2 because of we look at Vg is 0, then we know the value of R2 lah. If we know the value of R2 and R1 and Rx is the fixed value, then we can calculate for Rx. We can calculate for Rx. Okay. So the key is we want to try to measure the Vg so that it will have a 0 value. And then if Vg has 0 value, then R2 can be easily it show the value lah. It show the value and then we can calculate for Rx. So look at this one. Look at how the equation is formed. The most important, if we have this circuit, okay, you have to memorize the circuit. So R1, R2. Look at the way the Vg is crossing here, okay. R1 here and R2 here, okay. Maybe some people put it R3, put it here, R3 here and R2 here. It doesn't matter. If we change the value R2 and R3 here, so for this case, R3 will become the variable resistance, and R2 become a fixed point. For example, if you look at this one, sorry, if you look at the next one, okay, if you look at the next one here, look at the circuit here. So if you, sorry, if I can return to the previous one, look at this one. Okay, this is actually a input. Input fixed point. It's also fixed. Starting from point A until point C. It's a fixed point. Okay. So if you look at this one, so you have the same value. If I can redraw, this one. Okay. So this one is so this one actually E lah. E. So EI. Okay. And then so where's the G? The G crossing from here to here. is a G. So if we look at this now, if I can write down, here is the R1. Sorry, this here is the R2 lah. This here is R1. And here is the, is it correct? Yeah. So here is the R3. Okay, this is a variable, big variable, and then this one the R X or RRTD. Okay. So if you look at this, if I redraw this one, so we will see that actually the ratio between, can I change R2 here and R1, the ratio between these two, it must be equal as the ratio of this one and this one. Okay, so inilah so if you look at this one, so if you look at this, the equation, so it's actually a ratio between R1 and R2 equal to R3 and RT. I don't want if you put R2 over R1, so it must be equal to the Rx over R3. So if you change the position up and down, then we should be accordingly. You change the value of R lah. So again, R1 over R2 is fixed value, and then now R, if you change the, sorry, if Rx have a different value, increased value, so we must change the R3 so that it will balance and make sure that G value is 0. The G value is 0. So whenever G value is 0, that means we stop adjusting the R3, and then now we look at what's the value for Rx. Okay. Yeah. If I can delete this one, delete again. So hopefully you understand. So if we look at this graph here, sorry, if we look at this here, this one, it have R3 and R2 and R1 as the additional wires. So when I have additional wires, of course it will decrease the resistance. So if we want to include all these additional wires, so just include in the equation R3 plus R1, because R3 is plus R1 here, same circuit as R1. So RRTD here plus RRTD, okay, and R2 here it actually not involved in the in here, because actually it's not it's not connected to any resistance. So R1 and R3 is very important here. Make sure it's included in the equation here. Then we can calculate lah. We can calculate RRTD. So now this is actually how RTD being measured. So we look at the example. So again, if you look at this circuit here, so now try to put a G outside. Same, if you can put this here inside here. Same lah. This is creative way to confuse you. But the most important is to make a ratio. So we have a fixed voltage here. So now what kind of how can we create an equation? So of course the ratio between these two, R1 over R3, must be equal to the ratio between R1 over RTD or Rx or Rx. So just form the equation here. Just form the equation. So look at the information. Information said that the R1, R2 and R3 is fixed value 25 ohm, and then R0 is, of course, like I said, is the initial reference value. It's given 25 ohm, and the temperature, the early temperature also given. So it's a 0 degree. just with the so R1 is the variable resistance. So to make sure that G is 0, so we adjust the R1, and after we adjust and look at the G is 0, then it's found that the R1 is equal to this one, 37.36. So we know that R2 and R3 is a fixed 25 ohm, and then the R1 is this one, and then just fill into equation here. Okay, then you got RTD is 37.26. Of course, it will have the same value lah, because of this one R2 and R3 is the same value. So just a simple quick question. How can we want to double the sensitivity of the sensor? The answer is, because of this equation, you make sure that you put the ratio R2 over R3 double. For example, R2 so we let the R2 is 50, R3 is 25. So that if you put here, the ratio is 2 over 1. So of course, with 2 over 1, R1 need to be times by 2 lah. Times by 2. Then you can get you can have the RTD is what value? It's less kan? It's less because of R2 is 50. For example, R2 is 50 and R2 50 and R3 is 25. So of course this one is 2 times than RTD. Okay. So we have to if you have to move, variable temperature, variable resistance more in order to get a very small change of RTD. So that's if we put R2 larger than R3. If you put R3 larger than R2, we have a different effect lah. Alright. So the most important is, once you get the RTD, then you just include into the equation. So this is RTD. So RTD here, R0 is given, coefficient is given, and then T0 is given. Now we can calculate for the T value. We can simply calculate the T value become 126. 126. So if I ask you, this is something that you have to think about. We know the sensitivity is small input will give very big output. Input small, output big. So for this case, how to make it more sensitive? In other words, we want to make sure that small increase of temperature will give big increment of resistance, because we measure the resistance kan. So how can we do that? How can we manipulate all this value here to make sure that very small increment of temperature can give very large increment in terms of resistance? Let's say twice than this one. I leave this question to you. This is one of the questions that I asked in previous test. Right. Now we look at the last one example for the resistant type of resistor type of temperature sensor, which is the thermistor. The thermistor is a short form for the thermal resistor. It made of semiconductor, different than RTD. That RTD is made from the metal, for example, nickel, platinum, and so on. But this one thermistor is constructed from semiconductor. And then if we use semiconductor, now we need to understand that the physics of this one. For semiconductor, the increase of temperature, it will reduce the resistance. So you increase the temperature, it will reduce the resistance. That's how semiconductor works now. In the previous one, we increase the temperature, the resistance will increase. For this one, we increase the temperature, the resistance will decrease. Okay, so this is different between thermistor and RTD lah. Okay. So further, the coefficient of resistance. Sorry, before we go to this point, we go to the first point. Thermistor is extremely sensitive because of the resistance change very rapid with the change of the temperature. Small increment of the temperature, it will give it will reduce the resistance a lot. Okay, reduce the resistance a lot. It's about 10 times. 10 times. It's about 10 times sensitivity compared to the RTD. Okay. So in other words, if you look at, if I can summarize this one. Okay, RTD is small increase in resistance will give a small increase with the temperature. For thermistor, large decrease in resistance with the increment of the temperature. So it's like opposite between those two things here. All right, so this is the graph. So if we look at the axis here, increase temperature, the resistance, okay, will drop. Will drop a lot, a lot. This is it looks like linear, but actually if you look at the graph, the scale here, it's a logarithmic scale. It's a logarithmic scale. So suppose that it have a very sudden decrease of the temperature. Sudden decrease of the resistance with the increase of the temperature. All right. And then the curve is given by the value of beta lah, beta in terms of Kelvin. Okay, so this is actually the construction of the thermistor. Something like this. It's very small. I think it's very small. You can, if you want to look at the physical of this thermistor, just Google it and you can find a lot of pictures for the thermistor. The same with the RTD. If you want to look what is the RTD, how it looks like, just Google and then it will show you the type, the image of the RTD and thermistor. The thing is, for this one is it can be very small in size and sometimes can be very extremely small. And also it can be a large size lah. Of course, large size is easy to be done, but for the small size of temperature sensor, it's not easy. But because of this one is from the semiconductor, it can have a very small thermistor lah. So thermistor compared to RTD, thermistor have better for the dynamic range measurement because it has fast response, high sensitivity, and it rugged. Okay. So this is a equation for thermistor. Easy. R is the resistance value that we want what we want to look for, and R naught is the earlier value, original value of the resistance. Beta is depend on the beta. Okay, this one. Depend on the use the pointer. So the beta is depend on the it's given it's depend on the curve. Different material have different curve, and then we have this actually the temperature, and this one is the original reference temperature. So of course the relation that we want to look is the how it's R the resistance relate to the temperature here So I want to calculate. If we given all the value, then it's simply we can calculate. So R value, how can we get the R value? You can use this circuit. You can use this circuit. Basically, this is the equation. This is the equation. So the RT is the one that we want to measure. To find RT, you put into this equation. And then you simply can calculate the T . Alright, so for this circuit, either you want to use this circuit or this circuit, it's depend up to you. Both give this value . So think if we have R1, R1 is for example, if you use this circuit R1 here, and E1 is the one that we is given . Okay, EI is fixed value. Okay, R1 is the fixed value. R1 is fixed value. We can just fix the value for R1. What we do is we put measurement here. We measure the EI here, E1. E or the voltage along this resistance. You find the E1, then you put into equation because EI is a fixed value. It's a fixed value. You find this one. This one is fixed, given, and you measure this one. You can find RT RT. So the E1 is you can get from voltage voltmeter voltmeter. Alright. So there is another example here. I think this example I leave it to you to look at. If you have any question, that let me know about this one. But I will leave it to you to look at the example because the calculation is just easy, straightforward. Straightforward example, straightforward calculation. Just use the most important is use voltmeter to measure the voltage at this R1. R1 is a fixed value. You got E1, you got RT, you put RT into the equation, you find T. Alright. So a thermocouple is one of the temperature measurement or temperature sensor, but it use electrical base. Again, it's same type with the thermistor and RTD. It used electrical base, but this time this thermocouple it generates its own voltage. It have its own voltage that relate to the temperature. So how does it work? Actually, with thermocouple, if we have thermocouple is built by using two dissimilar materials. It joined together. If we look at the circuit here, we have A and B wires is combined together. So at the joint, we have two joints whereby the A and B wires is connect together. We have two joints. The first joint, the T1, is one of the joint that we use to measure, and the other one is T2. T2 is the reference junction. So if you can measure in the circuit, we put measuring device, potentiometer or anything that can read the voltage. You can get the voltage. The more temperature difference between T1 and T2, the more voltage that we can that it creates. Because by using two materials, there's physics behind this. There is physics behind this. That two materials, basically metallic materials, is a special special physics, whereby the electron will move from another material to another materials. Because of this, it creates its own potential difference. This the definition of EMF is electromotive force. Two materials combined together, it will create electromotive force. It's not actually a force, but it's actually is create a potential, so that when it have a potential a difference between the two circuit, if there is a current or electron, it will flow inside the circuit because of this electromotive force, okay, EMF. So EMF creates the potential difference, and then creates like so there is I don't know how to explain that one, but with the EMF, this the current will be able to flow inside. If the EMF is low, for example, if we have a material A and B, when it combine together, it produce low EMF. So if there is a current inside, still it can flow, but with a low rate of flows. So that's why we need to have we need to proper select material A and material B, so that it can create a good EMF. It can create a good EMF, and then the more temperature difference, the more EMF it will create. So that's actually the theory, the physics behind it. All right, so we go further so that we can see how does it works in details. Okay, so I frequently use the term junction. Junction, usually if you have thermocouple, you have two junctions. Like I said, you have one junction for the reference and one junction for the measuring, for the measuring device. So if you look at further in the text, if you look at the your slide further, you can see this is actually one of the example. Sorry, this is actually examples of thermocouple. There's so many type of thermocouple. You can just go to the any shopping platform, Lazada, Shopee, eBay, I mean Amazon. You can find a lot of thermocouples available, but you have to know how to pick the best thermocouple for your application. So how to pick it? How to pick the best? Let's go to the next slide. This next slide will show it's a fundamental of the thermocouple. Then you can have the idea which thermocouple is suitable for your applications. So if you look at the junction, in commercial thermocouple, you can see if you look at the junction here, it's actually consists of two materials joined together, and then we have metal C and the tip, okay, and then you have insulation to make sure that there's no external temperature involved that creates error to the measurement. So this actually at the tip of the junction, So why this kind of arrangement, we can see later. All right, so this, as I mentioned earlier, this is actually a fundamental circuit for the thermocouple. Two materials, we have T1 and T2 as a measuring junction and reference junction, and we have a location for the EMF measurement. So this is actually a location, or we call it measuring. We put a measuring device here so that it can measure the voltage due to the EMF, due to the existence of EMF. All right. So the main criteria is actually it must the T1 and T2 must have a deep temperature difference. If there's no temperature difference, there will no EMF and then no electrical current flows. All right, so this is very important. All right, so why the EMF produced during if we combine these two materials and form in that particular design? So actually because of this three main effect, which is a Seebeck effect, Peltier effect, and Thomson effect. But the most is on the Seebeck effect. Seebeck effect contribute the most of the EMF generation in the thermocouple. So it's actually it's very interesting phenomena. It's actually from the physics that we learn, that we know, and that we know this phenomena happen, and we utilize this phenomena in the measurement for measurement application. So the Seebeck is actually caused by the junction of the dissimilar materials. We have two junction of dissimilar materials, and at the junction we have different temperature, then it can create EMF. At the same time, with that dissimilar materials at that joint as well. At that particular joint, if Seebeck is if you have two joints, so it create EMF. If you can see at one particular joints in one side of joints, at that area, the Peltier effect happening. Yeah, so if there is current flow inside, okay, current flows at that area, in that dissimilar material at that particular points, it will dissipate or it will release heat. Release heat. So release energy. It can release energy or it can absorb the energy. So absorb energy, also it can turn into EMF. Okay, at that particular joint. So and the last one is Thomson effect. It's actually if in one line, in one circuit line, if you have two temperature difference, so basically it will have also a small EMF will be generated. If there is in one material, one long materials and one temperature on the other side, and the other temperature is in another side. So this temperature difference create a small EMF. So combine the combination of all EMF with Seebeck effect, Peltier effect, and Thomson effect, it creates a significant amount of EMF. That's very good for our measurement. For the temperature measurement. All right. So just a little bit history. Yeah. Seebeck effect found by Thomas Johannes Seebeck in the last decade. Last decade. It's a long time ago. Like I said, if you have two materials, you join at the end. Okay, and we make a two junction, so it will create its EMF in the circuit. Just make sure that T1 and T2 have a significant different temperature. EMF will flow. Now, and then Peltier found by John Charles Athanas Peltier, Mr. Peltier, is found that have two materials joined together, and at that area where the materials A and materials B join, it will have a heat transfer if there is current flow. This happened because of materials A and material B have temperature difference. We know from the thermodynamic law, if two bodies join together, combine together, touching together, it tries to have a uniform temperature. So how this uniform temperature can happen? One of the material will need to release energy. Otherwise, it cannot have a same temperature. So that release of energy, it's the bigger current flows. So currents will try to increase the materials temperature. The temperature need to be the same. So if temperature have don't have, if you have temperature difference, it will release the energy. You can use the Peltier effect for the heat generation. You can have, I mean, you use a Peltier materials, which is a Peltier material is actually two materials combined together. So Peltier materials you can use for the heating element. Heating element also you can use for the uh, refrigerator, because uh, not only it release heat, okay, it also can absorb heat, because of it try to make sure that the temperature have the same temperature between two materials. Either it release energy or it absorb the energy. So if it absorb energy, we can use for refrigerator. All right. So it's very nice temperature. Even you can go to the shopping platform. You can buy your own Peltier material, okay, or Peltier heating element. You go by that keywords, you can find it's not it's not expensive. It's very cheap. So you can do your own system project with that one. But the thing is for thermocouple, that uh, the heat that absorbed by the that material that material, where it go? It go to the EMF. It turn into EMF, electromotive force, and with the EMF, we can have the current flow lah. We can have the voltage generated. So that's the Peltier effect, and the Thomson effect. I will not. I don't want to re-explain again. So let's just look at the figures here. If we have long wires, so we have a current flow. Sorry, if we have T1 and T2 temperature difference, the more temperature is you have more significant EMF. Okay, so let's the thing is in the same materials. It is in the same materials with two different temperature, so it will create EMF, and then it will have voltage flows. But it's not many lah. It's not much. It's not much because that's why I said the most EMF is generated by the Seebeck effect. The least EMF is by the Thomson effect. All right. So in order for us to combine all this effect and then form the thermocouple, we need to use the three laws. Three laws to make sure that we can have a good thermocouple. It make this laws make the thermocouple available for measuring. Okay. Now, law of homogeneous materials says that actually it's related to the Seebeck effect lah. Seebeck effect or Peltier effect. You must have at least two materials for the construction of the thermocouple. Otherwise, there's no current flow lah. So that's actually a law. It must have at least two materials. Okay, two materials. And then intermediate materials. So for the intermediate materials, if simple, if T3 and T2 have the same temperature, like I said before, it have uniform value. So there's no current flow. Why? Because of everything create EMF, but with the same temperature, the total of EMF in that particular area, in that, for example, if you have area here, we have two junction here. Actually it's two junction. Okay. In these two junction, because of T3 and T4 have a same temperature, if uniform, it also creates its own EMF, but the total of EMF inside this area is equal to 0. So it's good for us to so this law, although it have two materials, it makes us possible to put a measuring device, but make sure that it have same temperature. Okay, same temperature. Otherwise, it can create its own EMF and disturb the reading from the other junction, T1 and T2. Okay. All right. So that's actually law of intermediate materials. Total EMF is 0 if the temperature is uniform. So for the next one is the law of intermediate temperature. So if you have to, if you have two circuit lah. So basically, um, basically you have two temperature. Okay. For example, T1. Sorry, if you look at here, T1 have other temperature, measuring other temperature with T2 as a reference. Let's say 0 degree, and this one is measuring temperature. And we have another circuit which is also T2 here, and T2 is the same temperature with the previous circuit, which is 0 degree, for example. And then the other T3 measuring another temperature. Okay, so we have 3 temperature here. But if you can combine the circuit, because of we know T2 have the same temperature, so the total of EMF is the combination of total the EMF from circuit E1 and then the total EMF from circuit E2. The total we can have E3 as the overall EMF. So that's actually a law of intermediate temperatures. So these 3 laws make possible for us to establish or to create this thermocouple measuring device. All right, so let's go further. So if you look at this, now it's actually the same basic circuit, but to make it practical, so we change your view into the circuit. Actually it's the same circuit as this one, the same, but we form it this way so that you can see where the potentiometer is located, okay, in that circuit. And then we have two materials A, which is chromal, and the second material is the constantan. And for this case, if you look at flow here, this one connect to the EMF reader. Okay, this one chromal connect to the EMF reader. Mean that chromal is the material B. Chromal is material B. Okay, chromal is material B because it's material B connected to the potentiometer here. Okay, so constantan is the material A lah. It's material A. All right. So the reference junctions we put into the reference temperature, which is if you could still remember, I mentioned about the reference temperature in the earliest part of our lectures about the temperature measurement. We have a fixed point. So for now we have 0 degree. It's easy to get a 0 degree. You put in the ice bath. Ice bath for sure it creates a 0 degree temperature. And the other junction used as the measuring junction. You can put anywhere you want to measure. That temperature difference create EMF and make possible to current flows and voltage increase, and it can be measured by the potentiometer. So for the so let's say we put more circuit, and then we add more junction as shown in the figure. So law of intermediate materials saying that although you have two junctions, additional junction, but that junction is inside the same temperature, the total EMF is 0 and it will not create any voltage. So it's the same. It's the same. So it doesn't matter how many junction that you create, put at the same temperature, it will not affect the temperature measurement. Okay. Sorry, it will not create sorry, yeah, correct. It will not create any temperature, any extra EMF. All right. So if I can go to the next one. Okay, this slide. What I try to explain here, actually, the temperature the reference at that reference area, we have two kind of reference. First is the temperature ice bath, which is 0 degree. 0 degree for sure it's 0 degree, and we also can use temperature reference with a constant environment or constant temperature, constant constant material or constant environment that have same stable temperature. It always consistent the temperature. Okay, it doesn't matter. So either use 0 degree degree C with the ice bath, or you have environmental temperature that consistent. Okay. If you use ice bath, of course it 0 degree. But if you use let's say environmental temperature, you must have another temperature sensor to measure that temperature. For this case, we're going to use thermistor or RTD. But thermistor have high accuracy. Sorry, it have very low uncertainties compared to the RTD. So better we use thermistor. Okay. But if you compare to the ice bath, the uncertainty for ice bath is lesser, a lot lesser than if you use environmental temperature. Okay, for example, using thermistor. So if you look at this slide, if you use ice bath, it's about 0.01 degrees C uncertainty. Okay, which is if you measure something, it may fluctuate. May fluctuate about 0.01 degrees C. But if you use environment temperature by using thermistor, it will fluctuate about 0.1 degrees C. All right, so that's why we prefer to use ice bath for the for research. But of course, if you measure something in the field practically, you cannot have ice bath. So you're gonna use electronic build reference junction by using by measuring the environmental temperature as the reference temperature. All right, so with that, you can see now we have for thermocouple, it will have many types, which is actually the type indicate the material combination that we use for constructing the thermocouple. For example, E-type have chromal and constantan, and J-type iron with constantan, K chromal and aluminum, S platinum and platinum, platinum plus rhodium and platinum, and T is copper with constantan. Each type is used for different applications, different temperature difference, different temperature range. So you must make sure that which type is suitable for your application. So it's another example, more details in terms of the type and then the details of the type. The previous slide is showing the temperature, the materials, but this one showing the range. For example, K, it can be used for 0 to 1100 continuous temperature measurement. Okay, for short-term measurement, it can be up to negative 180 to 1300. So for short-term, it can use for larger range. So with this table, you can find with each type with temperature range that actually for the thermocouple, and then and see we have a note as well at the end. So for example, E-type, it have EMF, very high EMF output. So basically this table help us to choose which type of thermocouple that we want to use for our application. All right, so now if you look at the thermocouple also have its own calibration curve. Still remember calibration curve. We have output and input, and the relation between output and input creates its we call it sensitivity curve, or sensitivity curve. K, if you remember, please look at the earlier slide that I have mentioned. K, the sensitivity curve or sensitivity value for any measurement, it have the same. Okay, the basically is actually a a slope of the linear line. If you look at the thermocouple, we have many types. For example, the first one, chromium versus constantan. Chromium and constantan, I think it's a type K, I think. If I look at it. No, it's actually a type E. If you look at here, it's a chromium versus constantan, type E. Okay, I think this one type J, I think. You can refer back to this slide. So each type has different slope. So different sensitivity. If you look at the chromium versus constantan, it have very, very high sensitivity, but the temperature range is short. They have a short temperature range up to, from this one, 1700 maybe. But if you use different materials, look at here, platinum with 10% rhodium versus platinum. I think this one, I think, if you look at the previous slide, is type S. Type S. You look at type S, look at it have very big temperature difference. I think most is it the largest temperature difference here. Largest range of temperature measurement. If you look at the graph, also look at this, actually a Fahrenheit. It's Fahrenheit, not degree C. If degree C, you have to convert. So it's up to close to 3000 Fahrenheit degree. So it's degree C maybe 1700 as in the previous slide. So different thermocouple have different slope, different sensitivity, and different range of measurement. But you can see for the type E ini have very high output EMF. That's more sensitive. Alright, so now we look at the example how to measure. This one come to the I think for me it's very easy, but straightforward, because every thermocouple has its own table. You can refer to the table to measure the voltage. So with this amount of EMF, actually it refers to what temperature that we measure. For example, if you look at here, the ice bath. Sorry, before I forget, the table that basically the manufacturer will give us a table. Basically, it use the ice bath reference, to create the table. So with this case, if you look at this case, one junction put in the ice bath, and the other junction for measuring junction, and when they look at the potentiometer, it have 9.669 millivolt EMF, and it is a J-type thermocouple. So what is temperature? What is actually temperature reading for potentiometer 9.669 millivolt? So if you look at the table for type J, you can go to manufacturer, go for the type J thermocouple. For this one, how much the EMF? It's actually 9.669. It's here. So it's here, meaning that it's 180. So this is 0 degree. So 180. Let's say if you read 9. For example, 9.83. 9.503. So it's actually 170 and 177. So 177 degree. If DMF is 9.503. Okay. All right. So that's how you get. Okay. Now we go to the next example. Let's say you use environmental temperature as a reference. Okay. For this one, you have to combine two readings. Okay, for this one, let's say if we put the junction, one junction to the environment temperature with 30 degree, 30 degree, 30 degree. I mean, the thermistor showing the 30 degree. How we know 30 degree? Because thermistor give us the value 30 degree. But the measuring junction, we don't know what value. But the reference junction is showing 30 degree. So we need to use, because of this, the table is made from the made for the junction with ice bath with 0 degrees C. So we need to add more into the value. So with 30 as the reference to the measuring temperature, the EMF is given as 8.132 millivolt. Okay, millivolt. So we cannot find the temperature yet, because if you refer to this one, 8.132 is here, somewhere in the middle here. So if this somewhere in the middle here, you have to do interpolation, interpolation. Okay. So now, because of that, we need to add actually from 0 to 30. From 0 to 30. So from 0 to 30, what is EMF here for 0 to 30? 30 is, we know the temperature. So 0 to 30. So 0 to 30 is here. So 0 to 30 is here. So it's 1.537. Okay. If the thermistor showing not 30, if this condition, if the thermistor showing, let's say 25 degree, so you have to add this value. 25 degree is 1.277. That one if the thermistor showing 25 degree. But for this example, the thermistor showing 30 degree. So this is the value 1.537. So you put here, you add with the one that shown by the potentiometer. So the total will be 9.669. And we know 9.69 is referred to the 180. So the 180, that's the actual T1 that we want to measure. So from the example, we learned that first, if we use ice bath, you can straight away get the value of temperature from the table. If you use reference temperature, environmental temperature, you need to add another fraction of EMF from the table, some fraction. Then we can add, and then you can have the exact value for temperature measurement T1. All right. So so finish about the thermocouple. So this fundamental of thermocouple mechanism and how to measure the temperature. Now we look at thermopile. Thermopile is just a pile of thermocouple. It's just a combination of more thermocouple. It's arranged in that way, in certain way, in a special way, so that it can amplify the EMF. Okay. Yeah. So how it arranged? Something like this, It arranged something like this. Make sure that T2 have the same temperature, reference temperature, and measuring temperature can be anywhere Anywhere, it's up to you. Anywhere. Okay. So it's actually amplify the EMF from millivolt up to volt. So the more thermocouple or the bigger thermopile, it can have more sensitive value, sensitive measurement to the temperature measurement. Okay. All right. So finish with the thermocouple. Basically, finish with the electrical type of temperature measurement. So electrical type, non-electrical type, all of this is contact measurement. We have to contact with the area or the body to be measured. But now we come to the next type, which is the radiation method. So this one is non-contact. Basically during the COVID time, uh, we always use non-contact temperature measurement. It use a laser to measure the temperature measurement. I mean, the non-contact is everywhere nowadays. The problem with non-contact is actually it's actually a relative measurement. So the uncertainty will be the lowest lah among the others temperature measurement device, but it can go higher range, higher than thermocouple. Okay. So let's see the pro and cons about the radiation method. It can go up to 1400 degrees C, larger range than the thermocouple. In fact, it can go up to million degrees C, like we want to measure the temperature of the stars, temperature of the galaxy, temperature of the black hole, any temperature, anything that, sorry, black hole we cannot measure temperature. We measure the side of the black hole. Black hole don't have any temperature because it's black. But the side of the temperature, black hole have a very bright temperature, very bright object due to the process of black hole eating that materials. It creates a lot of very bright light, so we can measure that temperature. Basically, the radiation method is either we collect the heat from the device, from the body of releasing the energy, or we measuring the brightness of the light that create by the bodies. Okay. So from that mechanism, we can see that two mechanism of how radiation method works. First, by collecting the energy, absorbing the energy, absorbing the heat, and the other one is by looking at the brightness of the object. Some object, it creates its own light. For example, the metal. If you heat the metal at the beginning, it have its own temperature, but at some points it start to glow. Start to glow from yellow, from the red, become yellowish and yellow and orange, and orange start red, orange and become yellow. At the end, it become so hot, it become white. Okay, so at certain point, any bodies will generate its own light. Okay, us also we can generate our own light, because if we burn ourselves, we can have its glowing temperature. But of course, at that time we died. So that's the concept of this. You read the slide and then it actually tells the same thing. Okay, it may be telling you the concept of why this radiation happened. I'll let you to read this one. Okay, maybe I pick up some points here. Radiation actually refers to the emission of electromagnetic wave, because only electromagnetic wave can radiate from body. It can move from the body towards the direction that we measured. It have a lot of actually radiation wave, but the most important that we actually interested is the photon. Because photon is a light stuff. It travel in straight line straight to the measuring device. Okay. So but not only photon. Photon is for the light, but there's a lot more radiation wave. For example, we have X-rays, ultraviolet, visible light, and any thermal radiation, microwave. All right. For example, this one. If you look at this, there's a lot of more radiation that radiates, that transfer from the body to the outside. Okay. All right. The visible light is the one that we see. Blue, green, yellow, red. We can use this visible brightness for the measuring device in that range. We can use also the microwave radiation to measure the temperature of the uh, uh, to the object that release microwave. All right, so I leave it to read this one. But I go straight to the sorry, to the pyrometry concept. So we have two concepts. Sorry, if I can. If you okay, I go straight to the methods. I hope that you can read the previous slide for the concept of the measurement. We have radiometer and we have pyrometer. Okay, so radiometer is basically a radiation detector. It actually detect of collect the energy that radiates from our body. It collect. So you have a mirror. For example, if you look at the figures here, it's a basic of radiometer. You have collecting lens. You collect the energy, heat or whatsoever, and it have mirror inside here, and it focus on one point here. That one point we measure that temperature using any kind of uh, measurement device. For example, thermistor, thermocouple, RTD. It's up to you. But it have the limitation of range. The limit is on the sensor that you put here at number 3 here. If you use the thermopile or thermocouple or thermistor or RTD, it depends on that range. The ability of that temperature sensor to measure the temperature. But for this, the radiation detector is non-contact. The range is up to the measuring device that we use here. But if you look at this type of measurement, is actually a relative measurement. So it have long way from the body, release energy, release temperature, and the temperature is measured by another device. So second, it's two kind of device involved here: radiation detector, and also the thermocouple, the thermopile, the thermistor or temperature sensor. So that's why it have like higher uncertainty than the other sensors. And then the second type is actually pyrometer. Pyrometer is actually, it uses the concept of incoming light. So incoming light, we measure the brightness and refer to the known brightness, and then by the comparison, we can find the temperature. For example, the brightness of a known brightness, we know that temperature of that known brightness. So if we can find another object that have similar brightness to the first one, so we can say that it have the same temperature as the first one. Okay, so this is actually the reference brightness. So any brightness come after that, we can compare to that one. So that's the pyrometer. We can use this one for measuring any glowing object that, of course, it's glowing object produce its own temperature. It has its own temperature. Like I said, some material, some bodies, it will start to glow if it receive that amount of energy or amount of energy due to the temperature raise. Okay. So that's the concept of pyrometer. I think there's actually you can read this one. I hope that you can basically understand the concept of pyrometer and radiometer. It's actually very, very simple. The other thing is actually good for the non-contact measurement, although it have a little bit high uncertainty, but it's good for the non-contact, and it also have relatively higher temperature range. All right, so basically I leave this to you to read at the end of the topic here for the radiation meter. So with that, I close the topic for the temperature measurement, And the next one, we're going to go to the next measurement concept, which is a pressure measurement. So thank you very much. Assalamualaikum warahmatullahi wabarakatuh.